All right, so this is 5.4, graphing a rational function. And it's more than that. It's also the story the graph tells us. So I like to say the rational function tells us more importantly than the other graph, a rational function, our job is to answer the question with the graph, what happens inside the box, and also what happens outside the box, here, 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 here. We want to answer that as well. So when I say the box, I'm saying that, there's a box of a certain size. Going 10 on the to the right and 10 to the left is pretty typical. Don't really have a typical number. I mean, 10 tick marks up and down are pretty typical, but in this chapter, you never know what they're counting by until you look at the graph. In other words, they could count by ones, and this would be 10, but they could just as easily count by tens, and this might be 100. So you have to look at what they're counting by here, but still, the box eventually ends. And if you have an asymptote, your job is to communicate what is going on outside of the box. We'll get to that, but my only point here is we're not just graphing like we're taking a picture of something and walking away. We are graphing to communicate what happens outside of the box. There's so much information. These really are kind of rich graphs, pictures. So the best thing to do is take the rational expression. It's always going to be rational, meaning numerator, denominator, and factor it to see if it cancels, see if it reduces, because you definitely want it to be reduced. All right. Once it's factored, you set the factors in the numerator equal to 0, and that will find the x-intercepts, because when the numerator is equal to 0, y is equal to 0. So you found that, it's essentially saying, well, I know y is equal to 0 when x is equal to, in this case, 1. If you set the numerator equal to 0, you'll get, right here, x equals. You set the denominator equal to 0, and you find the vertical asymptotes. You also find when the denominator is undefined, but that is where you find the vertical asymptotes. So in factored form, just set each factor equal to 0. We're used to that, but we just have to understand what it reveals. Next thing we're going to do is find r of 0. I'll find that on this here. Yeah, let x equal 0. And again, nothing new about, nothing, this isn't unique to the to rational expressions. When you let x equal 0, what you're doing is you're finding the y-intercept. And we lost track of the question here, but when x is 0, I have -1 over -9, or just 1 over 9. So this is my going to be, well, not just a point of the graph, but the y-intercept. Already found most of this. Now the horizontal asymptote, that's the only thing we haven't found yet. And there was just a kind of a menu, a little trick there, and that was, if you remember that when the numerator, if the degree of the numerator is 1 and the degree of the denominator is 2, you have the denominator is a higher degree than the numerator. And if that's true, the horizontal asymptote is just x equals, or just y equals 0, horizontal line of the x-axis. So y equals 0 is going to be the horizontal asymptote. And that was just from comparing, the actual question. That was just comparing the, 2 is bigger than 1. And so if the bigger number resides in the denominator, it's y equals 0. If it's a tie, then we have to look at the coefficients. And if the numerator is higher, there's another connection for that. So we'll get to those. But in this example, we know right away that the asymptote is 0. I'm not a believer in this kind of table where they're trying to do the above, below. And if I were interested in it, I would just draw I would just use this number line. And what is this number line? Actually, I wouldn't even use this particular number line. But what is this telling us? Well, I would just use. So here's what the author is trying to do with this table, I think. It's pretty unnecessary, but if you ask the question, when is this thing greater than 0? That will tell you when it is above the x-axis, meaning it's in quadrant 1 or quadrant 2. And if you ask yourself, when is it less than 0? We know it's in quadrant 3 and quadrant 4. I'm just going to say that's completely unnecessary because we have enough other ways of analyzing this. But they went ahead and ran the inequality. If you were going to do that, you'd factor this, x minus 3, x plus 3. You draw I guess I should have that one in there. You draw x equals 0. You distinguish between where it's undefined in the denominator and where it's 0. And then you just take a test point in each interval, and you would find out everything they said here. When it's minus, it's below the x-axis. When it's above, when it's plus, it's above the x-axis, below. All right. I'm not going to use that, though. Just there it was. I prefer this. We know the x. We know certain points. There's a lot more points than I thought we knew. We knew this point right here. When you put in 0, you have 1/9. And we know this point, 1, 0. Now, when I say we know these, is remember, it was our obligation to put in 0 to find this intercept. And we're also obligated to, because we know they're going to ask, to find the y-intercept or the x-intercept by letting the numerator equal 0. So it'd be this point. Of course, the asymptotes, because the denominator is equal to 0. And so here's my claim. My claim is we can graph this without anything else. I don't need this extra point, that extra point. Again, the book is just trying to soften this to make it kind of easy, but no. All right, so it's a couple of things we have to remember from an earlier section. When you have x minus 1 squared, the graph is just going to touch the x-axis. But if it's not squared, what is the graph going to do? It's going to cross at the x-axis. So I know this. Let me write the factored version of the function here. I know the asymptote created by x minus 1 is the type where the graph has to cross. And that's really all I need to go to run to the races here. If I connect points A and B, but cross at B, and then what's the asymptote there for? It's to tell us how the graph leaves the box. So it has to leave the box along the asymptote. Let's continue. I'm going to cross here. Remember, it's a function, so I can't do something silly like curve back like this and fail the vertical line test. The graph would have to leave the box here. Now, how am I so sure about this? Well, it can't turn the other direction because that would create another x-intercept. And I know I only have one x-intercept. I've already tested that. So I have this. Now, one thing I will refer to, and that is this, not this actual table, but the fact that it changed signs at every interval, at every point. Yeah, it's going to change signs when you graph. It's very important, by the way. When you have degree ones on those points, all right? If it's degree one, degree one, it's going to change signs. When would it not change signs? Well, it wouldn't change signs if I had an absolute value. It wouldn't change signs if I had a square. And it wouldn't change signs, I don't think we have any of these, if you had a fourth degree. All right, because these are things that make negative things positive. Here's the thing, you're not going to have any absolute values. We will have some squares. And basically what happens when it's a square, we already know it, it doesn't cross, it touches. And with that, what I'm saying here is that means it doesn't change signs. So it's negative because it's below the x-axis on this side of x equals 3. So if it's going to change signs, it has to be positive. If I'm not going to create any more asymptotes than I already have, it's going to fit in these perpendicular lines here, like a hyperbola. So the best we're going to do is just draw a hyperbola. And I say that's the best we're going to do because there are times when it wouldn't happen here because we already know there's only one x-intercept. But there are times where a graph will cross the asymptote and then kind of curve back up from underneath, involving crossing the asymptote inside the box. And the rule, by the way, the way I like to say it is, the graph can't cross the asymptote outside the box, if it's a reasonable size box, but it can cross it inside. So in this case, the asymptote was y equals 0, and it did cross y equals 0, inside. But it's not going to cross it once the asymptote, kicks in, once it the graph starts to leave the box. All right. But this would not be the exact shape of a hyperbola. There's a turning point here. It crosses, it kind of comes underneath. Yeah, even if that were true, like we could prove that with a graphing utility, we don't care. That's not our job. Our job isn't to have a really good graph. It's to have a graph that more or less covers the idea without trying to get alternate shapes. So since this one didn't have that, I maybe brought it up too early, but let's continue. So I know 100% sure that if the graph is going up and it's positive on this side, it's got to be negative because of the sign change. Again, why am I saying there's a sign change? What gave me this x minus 3? Well, I set x plus 3 equal to 0. And in the original problem, x plus 3 does not have absolute value on it. that would be a situation where if it's plus, it would stay plus, and it doesn't have x plus 3 to an even power on it. That'd be the only other situation where it would stay plus. So got to take advantage of that sign change at this factor. Let's look at the problem. All right. So the author goes through this problem, and looks like this is off a little bit, like it missed the dots. All right. Okay. And the author did it by plotting points. Plotting a lot more points than I would typically do it. It's very significant that the author missed that point there. Little piece of graph that missed the point. All right, so we want to connect those dots. We realize it's got to cross. We realize it's going down this one and up this one, because if it goes down on one side, it's going to go up on the other side, unless there's an absolute value that makes that happen. All right. Basically, they're just going to, well, I'll let them do it. They're just going to connect all those dots. Not dots. They're going to connect these little line pieces, all these arrows. But by the way, you notice all of these arrows are telling us what? They're telling us what the graph is going to look like outside of the box. That's the idea. What does this graph look like? Not just inside the box, but outside the box. So lots of slides. I really don't get it, but lots of slides later. Well, again, yeah, you want a book that over-explains instead of under-explains. But lots of work later. We got the graph that I had earlier. And back to this, I want you to understand. So I consider this kind of like reading a mystery novel, but figuring out who did it really quickly. We plot. So you can see what I'm talking about. Yes, we have to plot the intercepts. Yes, we draw the asymptotes. And a lot of times that's all we need, because once you start connecting dots, literally, this crossing here took me from quadrant 1 into quadrant 4, and I had no choice. I had to leave with the asymptote. Crossing here took me into this quadrant 2, and I have to leave the asymptote without creating another turning point, because creating a turning point would have necessarily created an x-intercept, and I know there isn't one. Leaving the box positive here means I got to leave the box negative here. So you just kind of chase the individual factors, the individual facts, and it will get you there. Another example, all right. So in this example, the degree of the numerator is more than the degree of the denominator, and so that's going to involve an oblique asymptote. Maybe not that oblique asymptote, but an oblique asymptote. I'm not claiming it's what equation that is. But we factor it, set this equal to 0, and that's going to tell us x equals 2, x equals, negative 2x equals 2. Set this equal to 0, x equals 0. Those are the answers to some important questions here. Do you remember, when the numerator equals 0, they do that. F of 0 is what they did here. No. When the denominator equals 0, you get a vertical asymptote, namely x equals 0. And I think in another video I called this the most obvious thing in the world. When you have a division sign, it's not that unusual that you divide. And that's what they did. They went ahead and divided and got a quotient of y equals x. This is the graph of the oblique asymptote. This is going to be y equals x. Now, they didn't continue with this minus 1 over x and get the remainder over the something. No, they just wanted the quotient part. Once you get the quotient, you know that's how the graph is going to leave the box. Plotting a few more points, which I'll do. All right. Let's look at it. So setting the denominator equal to 0 revealed the vertical asymptote. Long division revealed that number there. If I let x equal 0, it's undefined, it doesn't work. And when is y equal to 0? Well, it happened twice. It happened when, what's the equation? Yeah. When the numerator equals 0. Right? Y equals 0 when the numerator equals 0. So plus or minus 2. And again, I'm going to claim that's all we need. Once we have our asymptotes, once we have our intercepts, anything else is just fluff. Anything else is just doing more work than you have to do. All right, so I have this graph. There's a box. And this line right here is telling me how the graph leaves the box. Let me draw my other asymptote here. All right. That's what it does. That's what asymptotes do. So let me just finish it up here. All right. So I'm here, and here's an asymptote, and there's an asymptote, and my job is to leave the box with the asymptote. This is, there's two things here, the y-axis and the equation typo here, x equals 0. And I have to leave the box with that asymptote. So the asymptote just kind of tells me I've got that. All right, if I leave down here and it's negative, I have to leave up here because I need to change signs at the asymptote. Again, I changed sign at the asymptote because the denominator was x. Let's call it x minus 0. Right? To the first power, not to the second power or something else. So once again, I know the graph without several pages of analysis, including this whole sign idea and you know, a few other things the author did. Catch up to it. All right. Notice the degrees are the same. So the horizontal asymptote is y equals this 2 over that 1. So it's y equals 2. Setting the numerator equal to 0, I know that x equals 0 and x equals 1 are going to be my x-intercepts. And I know my asymptotes by setting the denominator equal to 0. R of 0 equals 0, one more point. This might be an exception to some of the problems that I've done before, in that the points themselves might not be 100% of the information I need. Set the, I had those points. I had this asymptote, and this asymptote, just from factoring and setting everything equal to 0. And I would say that I can't predict exactly what's going to happen here. In other words, it makes just as much sense to come curving through here, cross the x-axis, cross the x-axis, you know, cross the asymptote. That would certainly be a possibility. Or coming this way. which is a possibility. So I'll agree with the author in this one case. I need a little more information. And when I say I need more information, there is a reason for that. Normally, if I have two x-intercepts or any number of x-intercepts, the y-intercept is a separate point. And that didn't happen here. The y-intercept turned out to, and the x-intercept turned out to be the same thing. So need a little more information. So let's go ahead and probably the most logical point, I think, would be to put in -1. If I put in -1, I would get here it is, -2/3. And now follow me here. That means I'm off to the races. If I connect these two dots, and I have to leave the box along the asymptote without creating unnecessary curves or crosses of the x-axis, then I'm going to connect these dots and leave the box this way. Create a turning point so I can do that again this way. And if I'm leaving on the negative here, I've got to leave on the positive here. And if I'm leaving on the negative here, I've got to switch to positive here. Now, I'm going to draw this differently because, quite honestly, the best we can do when we have two asymptotes crossing like this is just to put well, I guess we can get it a little more accurate when we plot some points, but I'm going to say just kind of bend a hyperbola through there, because that's really the best we're going to do by hand. No way would I know it's not this curve that's just kind of bent in there and leaves the box with the asymptotes, and that one somehow better, unless they used a computer, because that's not at all obvious. So draw the shape you know. All right, this is a situation I talked about a moment ago where the graph actually does cross the intercept, the horizontal asymptote, and I'll exaggerate it here. So in reality, and again, it's only a computer that's telling us this, our graphing skills would not tell us that. Now, if you were taking calculus, you'd know, but would not tell us that the graph is going to cross the x-axis, not the x-axis, the asymptote, do a little turn, and then come back up. Still, leave the box with the asymptote, but underneath, from underneath. So that's exactly what happens, but that's going to be a mystery to us. We don't do turning points unless they're very special, very rare cases in this class. So give up all hope of finding that. It's not going to be important to us. All right, here's an example where they factored, and notice that if you reduce the problem, you're really just graphing this one. And what this means is there's going to be a hole in the graph. So this is what we graph, but keep in mind that x cannot equal 3. Now, -3 is still a legitimate vertical asymptote because it's part of the final fraction. But if it's 0 in the numerator and denominator, we cancel it, it does leave what we call a hole behind. Lots of plotting. All right. So find the asymptotes in the normal way. Find the intercepts in their normal way. Setting things equal to 0. And again, my claim is we're ready to graph even if the author isn't. You've got these two dots. Leave the box with the asymptote. You cross here. Leave the box with the asymptote. Draw the function. You have this here. Draw a hyperbola. that fits in that perpendicular lines. Again, I'm using the idea that the asymptote tells us how the graph leaves the box, and I want to cash in on that. So, did they ever get it? So many pages. All right. The one thing I didn't talk about was there's a hole at 3. So remember the problem actually had an x plus 3 or x minus 3 that got canceled in both the numerator and denominator. So we have to acknowledge that was originally part of the problem, and therefore we put that hole. All right. Well, let me go ahead and just finish this one example then. All right. So here's something interesting. Notice how this is negative and it's still negative. So this asymptote, the x minus 2, has to be squared or an absolute value or some exponent, but fourth power or something. But this is what it looks like when the signs don't change. The signs did change here. So this is going to be x plus 4 not squared. All right. And because I'm looking at asymptotes, those are going to be in the denominator. The intercepts are telling, looks like there's an intercept at 1, at -1 rather, and it's the type where it doesn't change signs. So what would give me that 0? It would be x plus 1, and that has to be squared. This is x minus 3, and that has to be not squared because I crossed the x-axis. The one thing I haven't talked about is the asymptote, but let's see how they piece this all together. Turns out the asymptote y equals 1 is consistent with this equation because it's degree 3, degree 3. In other words, if I were to multiply this out, I'd have x cubed. So equal degree in the problem. All right. So they gave us the question, and we came up with the equation. Yeah, we're not going to be doing this because it requires a graphing calculator. So no, I put this in red, not required, not required, not required because of the graphing calculator. But basically what they did was they found the equation of all of the aluminum in an aluminum can and kind of played with it. But well, that would be it. So everything in red, again, I highlight it in red because it's not something we're going to cover. So yeah, that was a long section, but I think it's important to take a few of these examples and really get to know them, so you can graph things in something with an asymptote, and not just a picture of what you have in the asymptote, but we're using all of this to tell a story of what happens to the graph over its entire domain.